Good morning, everyone. What we have here is a differential equation, dy dt is equal to ky. So it's when our rate of change y with respect to time is directly proportional to y, and k is a constant of proportionality. What we want to do first is we want to separate our variables such that our y's are on one side and dt and k are on the other side. So to do that, I'm going to divide y from both sides, and then I'm going to, after I divide both sides by y, I'm going to multiply both sides by dt. So we have 1 over y dy is equal to k dt. Now that our variables are separated, we're able to integrate both sides with respect to y and with respect to t. What we end up with is the natural log of the absolute value of y is equal to k, our constant, times t plus c. We're getting that t because, of course, we're integrating with respect to dt. At this point, we want to be able to condense this such that y is by itself. So there's two ways of doing that. I'm going to show what I think is maybe the harder way to understand, but it looks cleaner. So what we're going to do is we're going to take the natural log of the absolute value of y and keep that as is. And for each of these terms, k, t, and c, I'm going to take the natural log of e because this represents 1. I'm going to raise that, or erase kt, like this. Natural log of e raised to the c. And again, this is being done, class, so keep my equation balanced, and then I could use my rules of natural logs in order to combine these, because whenever we have addition between natural logs, that means it's really multiplication. So this becomes the natural log of e to the kt multiplied by e to the c using our rules of natural log. And then at this point, since we have both sides of our equation have natural log starting it, we're able to set our inner terms equal to one another. Okay, we can also take e to each side, but it's implied that these would be equal to one another. So I'm going to say y is equal to e to the kt times e to the c. And then from Friday, what we learned was, well, e to the c is just some number raised to some constant. So we're going to rewrite this as big C instead of e to the c, multiplied by e to the kt. And now we've just come up with a general equation for some exponential growth function. Next, this is just showing what inversely proportional would look like. And as you see, it's still dy dt, but our y is in the denominator rather than the numerator like it was previously. We are not going to derive anything for this. This is just for you to see that inversely proportional shows this relationship with a differential equation. On our next slide, what we'll see is we'll see that general equation again, y is equal to c times e to the kt. And just note that c is some initial amount, k is the rate of growth, t is our time, and y is our new amount after some given time. So we're going to now dabble with radioactivity, which you deal with in chemistry. And we have radioactive decay, which is measured in terms of half-lives, as most of you should know from chemistry. It's the number of years required such that some sample of atoms decays by half of its total amount. And you see that k is equal to the natural log of 1/2 divided by the half-life. How this has all come about is, well, let's say that we had 20 of some starting amount, and it was e to some kt, after some amount of years, I would cut in half. I would go from 20 to 10. So with that being said, when I divide both sides by 20, this will reduce to 1/2. And really, for any numbers that I choose for my initial value and my final value, it's going to reduce to 1/2 for any half-life. And that's why this will always be the natural log of 1/2. Because at this point, I would take the natural log of both sides. So I'd have the natural log of 1/2 is equal to kt, because again, the natural log of e is 1. And then if we want k, we're dividing by time, which is the time for 1 half-life. And you see, this is our proof of how that constant for some half-life is the natural log of 1/2 over some time period t. Moving on. We're going to write and solve the differential equation that models this verbal statement. The rate of change of p with respect to t is proportional to 10 minus t. So I would give yourselves a second to pause the video and try it yourself. So how we do this is we take dp dt, and because it's proportional, we saw before it was k times dt, right? Well, we have k, but our function this time is 10 minus t rather than just nothing in general, dt. We want to make sure that everything, and sorry, multiplying dt to both sides, that's why it's times dt. So we want to make sure that dp is on one side and t is on the other. And once it is, we can integrate both sides. So we can integrate dp, and when we integrate k times 10 minus t dt, we get p is equal to k, and then inside of our parentheses, it's 10t minus t squared over 2, and then plus c. And that's it. You don't have to do anything more than that. Next, it says complete the table for the radioactive isotope. So isotope is Ra, which of course Ra represents radium. And what we want to do is figure out what is the initial quantity of this sample, and we also want to figure out how much do we have after 10,000 years. So we'd be using y is equal to c e to the kt. That's our exponential function. And since it's a half-life function, we know what our k is because we derived it before. So our final amount is 1.5, as it shows up here in our table. 1.5 grams is left over. We want to look for what's our initial amount. And we have E. K is, remember, it's the natural log of 1/2. That stays consistent all over our half-life years, our time. So 1599. So that becomes our exponent k. So the natural log of 1/2 over 1599, and then our time was 1,000 years because that's what it says in our table. So in order to solve this, all we have to do is get c by itself. So it's just 1.5 divided by this whole thing, e to the ln of 1/2 over 1599 times 1,000. Just make sure you're careful with parentheses here and you substitute your values incorrectly. Otherwise, you will not get our c value. Our c value is 2.314 grams. After this, we're going to use this c value to get our amount after 10,000 years. So we start with y is equal to c e to the kt again. And we're looking for the amount after 10,000 years. We know our starting amount is 2.314. E to the natural log of 1/2 over 1599, the time for a half-life, multiplied by 10,000 years. And when we substitute all that in, we get 0.0303 grams. Next, now we have a bank problem. And with bank problems, A is equal to principal times e to the RT for something that's compounded continuously. So our initial investment is $20,000. That represents our P amount. Our rate is 0.055, and we want to know time to double. And because it's doubling, that means our A is going to be 40,000. So I'm going to set this up. 40,000 is equal to 20,000 e to the 0.055, because that's 5.5%, times t. When I divide 20,000 by both sides, I get 2 is equal to e to the 0.055 t. Next, we'll take the natural log of both sides. So we have the natural log of 2 is equal to 0.055 t. And then dividing both sides by 0.055, we will get our t amount. And the time it takes for this bank account to double is 12.6 years. And then it's asking, what's the amount after 10 years? So we want to know what's the A value. So all this is substitution. We start with 20,000, e to our rate of 0.055 times 10. And A is $34,665.06 after 10 years. Next, the population in millions in Egypt in 2007 is 80.3 million. The expected annual rate of change of population, K, is 0.017. Find the exponential growth model, P is equal to C times e to the KT for the population by letting T is equal to 0 correspond to the year at 2000. So with that being said, we want to know, well, what's the initial amount at the year 2000? So we know 7 years after the fact that our population is 80.3 million. We don't know what our starting population is, but we know our rate, our K value, is 0.0117, and we know it takes 7 years for us to get to this amount. So just like the problem from before, we want to get C by itself, so we're just going to divide by e to the 0.017 times 7 to get C, and we find out that our initial amount is 71.3 million people. So our equation is P, the population, is equal to 71.3 million e to the 0.017 times T. And the last, use a model to predict the population of the country in the year 2015. So we want to know, what is the population when we start with the 71.3 million, e to the 0.017, but it's in 2015. So how many years after 2000 is that? Well, that's 15 years after the year 2000. And through simple substitution, we get 92.01 million. I hope you found this video helpful, and hopefully I can get these other videos recorded and finished. Thanks.